this exercise episode, I would like to do together with you an exercise because it is very interesting. And I have to carefully look at it to see what we can learn from that. There's an exercise from chapter 3, section 3.2 of textbook of Boys at the Prima. It has to do with the Wronskian and linearly the independence of solutions of a linear homogeneous differential equation. So it goes like this. It is a request to prove something, namely the following. The statement is this: prove that if y1 and y2 have a common point of inflection on I, then they cannot be a fundamental set of solutions on I unless P and Q are 0. So I just copied the assignment as it is stated in the book. Now, of course, if you see this totally out of context, it doesn't make much sense because all kind of quantities are in this statement but are not defined. So you have to browse the book a little bit or just be familiar with the content to be able to guess more or less, to interpret the question, to guess what the meaning is of the various symbols. But if you browse that section in the textbook, you can discover what the meaning of P and Q is. P and Q are the coefficients of a linear second order homogeneous differential equation. So let us write that down so that we see at least what the meaning of P and Q is. So I write down linear homogeneous ordinary differential equation. I use an acronym. It looks like this. In the standard form, we always have a coefficient of the highest order derivative normalized to 1. So that tells us that there's no 0 here. There's no. So then I have the y prime, and the p that occurs in the assignment is the coefficient of y prime, the first order derivative of y. And the q is the coefficient of y itself as it occurs in the differential equation. And we talk about homogeneous differential equations. Why? Well, we talk about the fundamental set of solutions, and that is terminology that applies to homogeneous linear differential equations. So apparently the fact that I talk about solutions, a fundamental set of solutions, that implies that the assignment is about the linear ordinary differential equations, standard form of that, and then the standard terminology and notation in the textbook is that P and Q are the coefficients of the y prime and y. So that is that. Now we have to prove something. If there would be two functions known and that together form a fundamental set of solutions on I is some interval, thus the domain of those functions, the domain in which the functions are well defined, and that is typically the domain which the functions P and Q are well defined. So these are functions of X, so slight notation that I find convenient. Actually, I adopted it from the Wolfram programming language. If you want to emphasize that something is a function of X in this case, I use these square brackets. cannot promise that I will always be totally consistent. It is also a bit counter to the convention in textbooks where they always use round parentheses, so parentheses. The disadvantage of that is that you also use parentheses to indicate the order of operations, and also so that can be a kind of bit confusing and even ambiguous. So if you really want to emphasize that something is a function, or if I use these square brackets, so that is the notation. We have p is a function of x, so it's not a number, but it's a function of x. And that means that you could not solve this equation because p and q as functions of x are not even given. If they would be if you would know that they were numbers, you could just solve the equation. It would just be a ordinary differential equation with constant coefficients, but no such thing here. So it's quite general, but even then, the situation that we have to consider is that there would be two functions, y1 and y2, that would have a common point of inflection in I, and that would we have to think about them. Can there be a fundamental set of solutions if they would have a common point of inflection? Now then we also have to know what a point of inflection is. I'll come to that. But first let us focus on what the assignment is. We have to prove something. Now how do you typically go about that? Of course, an exercise in a textbook is well designed such that you can achieve the goal. If you use the material from the section that the assignment comes from, so we have to use what we learned in section 3.2, the initial section of chapter 3. And if you want to prove something, that is always based on assumptions. So you have to carefully watch out in the assignment what is actually given. That is what you know. And you use that, and from what is known you derive the conclusion, and the conclusion is over here. Apparently it is if y1 and y2 would be fundamental solution, then that implies that p or q is both p and q are 0. Then. That's what it says. If y and 1, 2 would be a fundamental solution, then both p and q must be 0. So that is what we have to derive logically. So it becomes clear that it is an implication. So apparently we should start from the assumption that y1 and y2 is a solution. Both are solutions. So let's write on that. That is simple enough, but that is given, and apparently we need it in the proof. So we write down if y1 is a solution of, and I develop some notation so that I can make references to what is on the paper, so I can make a reference to this. You could number it, but let's use an acronym. So I put labels between parentheses and I say this is the homogeneous equation HE. So now I can make a reference. If y1 would be a solution of the homogeneous equation, then now that just means that if you substitute it, that would give 0. That is the very definition of a function being a solution of a differential equation just means for all x. For all, this is a symbol from predicate logic. This is a kind of capital A upside down. A stands for all, and it also looks a little bit like V. So for, you might say, so for all x. For all x, if I substitute the y1 into a differential equation, I would get 0 because it is a solution. That is the very definition of a function being a solution. So that is the definition of a solution. Now, what else do we know? What else information could we use? Well, I was mentioning here a point of inflection. If y1 would have a common point of inflection, I should have a point of inflection in the first place, then y1. So you have to know what a point of inflection is. Now, that is a point where the curvature of the solution, if you plot it as a curve, the curvature is 0, it vanishes. So the second order derivative vanishes. So I write that down as well, and if let's say x0, if I consider it as a function of x, if x0 is a point of inflection of y1, then I write it here, y1 x0, the curvature there, the double derivative would be 0 then at x0. Now I start to number, so I call this my equation 1, that would be 0 if you would number it, and then I call this 2, and now say if both logic, if both 1 and 2 would be true, so both y1 would be a solution and it has a point of inflection at x0, then this will be 0. If I would substitute x0, I get to 0 there. So then the situation would be, if I would substitute x0 for 0, then I would get p at x0, y1 at x0, y1 prime, that is, and then q at x0, and y1 at x0, that would be 0. So I have a third expression here. So now I have used what is two things that are suggested in the assignment. Consider solutions, y1, and we will also have y2, that have a common point of inflection, so they have a point of inflection in the first place, each of them. For y1 I have derived the consequence of that, that is equation 3. There. Now, and I write shortly, similar for, when similar for, similar for y2, so if that would be a solution, I would substitute it, I get the same expression, but on y2 substituted, and if that is also also has a point of inflection, moreover the same. That is what it says. I have a common point of inflection, so it has a point of inflection at the same position. That is a common point of inflection. Then I would, for y2, have this same equation, but for y2 as well. The derivative of y2 at x0 at x, and the value of y2 at x0 weighted with q added to that weighted with p, that would also be 0. See? So, if you reflect on what we have been doing, what I've been guiding you through, it is a matter of carefully studying the assignment, which is only 2 lines in the textbook, figuring out, looking up, or remembering what the meaning of all the words is, everything that is given, and you use that step by step and write it down and derive consequences from that. Wait a minute, my sunscreen is going down, so let's do something about it. I'll do that. Whoop. Otherwise it gets a bit dark and we get interesting color of the workout. But this is alive, so this is real light. And if the sun starts to shine, the sunscreen is going down. You get this. All right, but here we are. Now, what's next now? Yeah. Then there's talk about the fundamental set of solutions. They cannot, so given to have to prove that they cannot be a fundamental set of solutions unless. Now you think about the logic, it says if there would be a fundamental set of solutions, then apparently P and Q must be 0. That is the meaning of that unless. Unless. If y1 and y2 would be a fundamental set of solutions, then P and Q must be 0. So we write down, I'm going to use a next ingredient, so I'll put a thin line here. And write down if y1, y2, when I write a set, so this curly braces notation, entities in curly braces, really means your set, would be a fundamental set then, a fundamental set is a set of 2 solutions, so they have to be solutions that is totally analogous, but is really the same mathematical structure as in linear algebra if you have a basis. A fundamental set of solutions for a linear ordinary differential equation as we have here, here, is a set of solutions, the linear combinations of which span all possible solutions. So the span of this would be the span of this fundamental set. The span of the fundamental set would be the general solution. So it would be a basis for the general solution. And for two elements to be a basis, they have to be linearly independent. And for that, as it regards ordinary differential equations, linear ordinary differential equations, we have the criterion of the Wronskian. And that is very analogous to having a determinant of a set of vectors as you have it in linear algebra. If you would have, let's say, a three-dimensional space, you would like to span it with a basis. Now you need a base. You need three vectors, or less than three. You cannot span a three-dimensional space. Moreover, they have to be linearly independent. Now there's in linear algebra all kinds of ways to test that, to assure that a set of vectors is linearly independent, but one way of doing it is to use the determinant. And the determinant of those, so you put them in the matrix and as columns or rows. Calculate the determinant, and the determinant must be non-zero, and then the vectors are linearly independent, and they span a space that has the dimension that is as large as the amount of vectors that you have. It means you have to have a square matrix in order to have a determinant in the first place. Well, for functions here, we also need, if this is to be a fundamental set of solutions, so it can serve as a basis for the solution space of the linear differential equation number HE here. Yes, they have to be linearly independent. And for that we have the criterion that the Wronskian is 0. So let's write that down. I write it there then. Wx must be non-zero. Did I say that? It must be non-zero. To be independent, it must be non-zero for all x. But then we have the wonderful theorem by Abel, from which you can conclude that if it is non-zero for some x, then it will be non-zero for all x on which the differential equation is well defined. So the coefficients are non-zero. This leading coefficient should be non-zero, but it is normalized, and otherwise the coefficient should be continuous for all x. So, but from this it follows, so it should be non-zero at that point of inflection, because that is in the interval. So, that is, it's a Latin abbreviation, with est, that is, and now I write the definition of a Wronskian for this expression, and that is, to make a Wronskian you just write the functions, and they are at point x1, for x0, at the point of inflection that we have in mind. And you form, so you write the solutions as the first row, and you form a square matrix by adding rows that contain the derivatives. So you start at the function value itself. Say n function, I have two functions here, but you could do it for n. Chapter 4 discusses the theory of nth order differential equations, and then you have n function spanning the general solutions and the Wronskian is n by n matrix. So you write n solutions and then the derivatives until you have a square matrix, because you need the determinant and then the matrix has to be square. So that is a heuristic way to remember how many rows you need and hence how many derivatives you need. So this you start with the zeroth, which is the function itself. So you will have the highest order derivative is one order lower than the highest order derivative in the differential equation. So up to 1 here, and not 2. Now the square, now we can write that this must be non-zero, but, well, let's see what that means. The determinant from linear algebra is this coefficient times that one. So this is the y1 at x 0, y2 prime at x0 minus, and now minus the elements at this diagonal, x0, y2, x0. And that must be non-zero. That is this condition that if there would be a fundamental set of solutions, then this Wronskian must be non-zero at each point, so at x0 it must be non-zero. This expression. So this is the definition of what the Wronskian looks like. And this is my statement that they must be, if they are a fundamental solution, then this must hold. Equation 5, that is. So we have now derived 5. If it would be a fundamental solution, then this would hold. So now we know something, and we have used from the assignment the fact that we have to consider fundamental set. So now it looks like that we have used everything that is given in the assignment. We have used that they are solutions in the first place. That was here. That they have a common point of inflection. That is common, because I have x0 here and there. So it is both y1 and y2 vanish. That's the second order derivative of that. Vanish at x0. So both satisfy these equations, two equations, 3 and 4. And then we have to consider the possibility that there would be a fundamental set of solutions. Now then we also satisfy that. So that is as much as I can discover in the phrasing of the assignment of things that are given. So we have to deal with this, and apparently from 3 and 4 it would be possible to derive then that if all this is true, then both P and Q must be 0. So somehow we have to combine these three equations. Now, to do that, I have to use this given that. I think what is a good idea to do, if you think about it, you see the minus here, so probably we need to subtract something. If I would multiply this equation by y2 and this one by y1 at x0, well, you see that these terms will be equal. The result will be equal if I subtract that. This cancels, and what I would get is P0 times that one times y2 and this one times y1. And that looks like expression 5. See? So let's have that. Just write it, so we can do it very briefly. So now I say, well, give it a bit an informal flavor, right, as well. I'll make a kind of an expression, a notation of what I want to do. I say expression 3, y2 at x0 times expression 3 minus I go and do the other way around. If I look at it, because then I get exactly that. That's maybe easier or more kind of pleasant. I say I go a pick 4, I multiply that by y1, x0, and I subtract 3 times y2, x0. Up. Now, as you see, y1 times 4 and minus y2 times 3, these terms cancel, so what I'm left with is a common factor p0, p at x0, so, well, p0, p at x0 times, yeah, as I say, 4 times y1, so that is y1 x0, y2 prime, x0 minus, that is this minus, I get the y2 x0 times what is in 3, that is y1 prime at x0, that would be 0. If this is equal to that, that is equal to that, the difference is equal to the differences, that is 0. 6. So that follows from 3 and 4. This. So we've used 3 and 4, aiming to apply 5. It is inspired by 5, but we have not yet used 5. It is inspired by 5. But 5 says that this is exactly what is here. y1, see, y2 at x0 times minus this expression is exactly that. And 5 says that this is not equal to 0. And then this together implies if a product of two things is equal to 0, that is what 6 says. Product of those things is 0. And 5 says this is guaranteed to be not 0, because if you look back why that is because if you assume y1 is a fundamental set of solutions, then this is not 0, and then apparently if this is 0, then px0 must be 0. Hence, px0 must be 0. That's implied. And in order to keep track of the logic, I say that is an implication, and I can write there from which it follows, and that is 5. That is also here, but 5 here says this, and 6 together. 5 and 6 together imply then that px is 0. So that says very briefly, you might write it down in words again, but it is now on paper. It says in the end, if y1 and y2 form a fundamental set of solutions, then you have this. and have a common point of inflection, that is this, then px0 must be 0. Now 6 is essentially, so hence 6 is essentially the consequence of 3 and 4. This is the and 5 implies px 0. So now we have proven shortly what is if they have a common sense point of inflection and they form a fundamental solution, then P must be 0 at x0. So apparently that is the consequence. The 0 at x0, that's the meaning of that statement. We also have to prove that Q is 0. Now let's see. Now then we have to, so this was kind of suggested, but you could of course in the same way. Now we want to derive a similar conclusion about Q, so we have to get rid of these terms. Now that can be done if you multiply y3, if you multiply, let's say 3. Now I want to, if these terms I want to subtract them again like we did here, but I want these terms to cancel. Now then I have to multiply this by y2 prime at x0, and I have to subtract 4 this equation times y1 prime at x0, because then I get in both p times y1 times y2, and here I get y2 times y1, and that is equal, so if I subtract them these terms cancel, and we are left with Q is common, so I pull it out of parentheses, because this is multiplication of expressions, so this is a common parenthesis. Now what did I have? Well, 3 times y1, that is there, so y2 prime, that is what I multiply with here, what is that, minus, and that y2, that one, y1, this is the closing parenthesis of that, and that is 0, because I'm subtracting these expressions. That is equal to that, that is equal to that, so this is equal to the difference, and 0 minus 0 is 0. Now, and then again, this again is 5. See, y1 prime over here. This one is that times this. Oops. 0. So 5 says that this is not 0. That's what 5 says. And hence again, this is our 7th. Well, let's say that this is our 7th result together. Then this will be 8. So 5 together with 8. And this again. Eight is again the consequence of 3 and 4. See, because what I do, I have 3 and 4. Now I do no more than an algebraic manipulation. So 8 is really the consequence of 3 and 4. And hence, these 3 given things imply 8 says this is 0, 5 says this is not 0, this is a product, so hence this factor must be 0. See? Now, hence, summary. Summary, it is really logic. If this is true and that is true, if the same assumptions apply both and this, then I have that 3, 4, and 5 imply, that is the logical implication, that says if this is true then that must be true, and that is 3 of 9. A rubber, make it clean. And 8. Now, maybe put it, of course the same, but let's put it as a sort of final result. 8 and 9. In words, if 3 and 4 says y and 1 y1 and y2 are solutions of the homogeneous equation and have a common point of inflection, then and they are linearly independent, that is 5. And they form a fundamental set, that is 5. And they form a fundamental set. Right. Then both P and Q must be 0 at x0. Now you see there's kind of a vagueness in the assignment. because we arrive at the conclusion that P and Q are 0 at x0. That was not specified, it just says prove that they are 0. Now we know what it means. Oh. I have to put a little bit up there. So, what we can derive it is that the P and Q are 0 at x0. No, they are 0 at x0. So that is what it says. That is what we arrive at. So in summary, if we take a step backward, what you learn from this, doing this together, is how to do such a proof. You carefully have to study what is given in such an assignment and make use of all the ingredients that you can discover that are given in the assignments, and then set up a logical reasoning, of course, using what you know from the course material, from the textbook about those givings. So what happened? We discovered that they talk about point of inflection, of course, then you have to figure out what that means. In an exam setting, I would specify that, because it's formally not part of this course to talk about what inflection is. I would specify that. But you have to use it. Now, what a fundamental set of solutions is, that is part of the learning goals of this course. So that in an exam setting could just be given in this way, and then you have to know what that means and what mathematical statements you can use to formally write it down. Have a statement that implements that concept, given things that you know about the situation. Fundamental set of solution means this. It's not a definition, but there's a theorem that says if this is the criterion for a set to be fundamental, functions have to be linearly independent, and you can check that by Wronskian. Now, what I recommend is to keep in mind the analogy with linear algebra. That will be throughout this course, because over and over again we will be developing the theory of differential equations, but almost everything will be about linear differential equations, and they are understood so well because they are very closely analogous to things that happen in linear algebra. It's actually the other way around. Linear algebra is kind of an abstract theory of linear structures in general, and that includes matrices, the matrix calculus, or vectors in geometrical Euclidean spaces, or function spaces. So all those have the same structure, and in mathematics that has been described in a more abstract way, and that is linear algebra. That is about that structure. So that is applicable here. So we will use it. So remember that the concepts from linear algebra will appear over and over again. They will surface over and over again. And here's one. The Wronskian is closely analogous to the determinant in linear algebra, and here we use it. So fundamental set is that determinant-like criterion for linearly independent sets. It just says there must be some determinant that is non-zero. And mind your logic. So write down what follows from what, the implications, and think about implication. Implication means here, for example, in the end result. Here. It says if statement 3 and 4 are true, so let's have it. So now this the image. If statements 3 and 4 are true, so if there would be a common point of inflection, and there would be 5, so there would be a fundamental set of solutions. Then P, then Q to both be 0 at x0 at that point of inflection. So that if-then structure is the if-then logic is here, the implication. So you could think of all kinds of variants of this assignment actually, like assume that Q is not 0, nowhere. Prove that there can be no set of fundamental solutions that has a common point of inflection, for example. That is the inverse of that logic. If that is true, then if this is true, this combination of conditions is true, then this conclusion must be valid. The right hand side, this conclusion must be valid. That means if it is given that one of the elements of the conclusion is not true, then the preconditions can also not be true. See? So, given the logic of the reasoning here, you can think of all kinds of variants on this assignments. So, reflect a little bit on that so that you will be able to handle all kinds of different variants of this assignments. Alright, I think that is as much as we can extract from this assignment, so thank you very much for your attention. My pleasure.